All right, we are recording. We are going to have an evaluation survey for you at the end of today's session. You'll be able to get a certificate of attendance for today's session. That link will be a SurveyMonkey link. It'll be in the Zoom chat. That evaluation and certificate of attendance, it allows you to tell us maybe some other topics. Maybe you want to get into a little more detail on something in design or something else regarding asphalt. We'd love to hear it, and we'll ask Chuck to come back and talk about that in the future. We are using Zoom, so we're going to be using the Zoom chat to give you some resources throughout today. I'll put the slides in and such, as well as that Zoom or that SurveyMonkey link. But I also really encourage you to use the Zoom chat. If you have questions, I will interrupt Chuck as he's going along, and I will ask those questions for you. We also have the Zoom Q&A set up and available to you. If you have a question that you would like to ask anonymously, maybe you're shy, maybe you think it's a dumb question. There are no dumb questions with this, so please ask them. I guarantee if you have that question, somebody else in this large group of folks also has that question, so please ask those. You can direct those just to me. I also want to let you guys know that we have closed captioning available since we're using Zoom. I know some of us have stood around heavy machinery a little bit too much without earplugs in, so that might be valuable to you. It should be available in the Zoom ribbon on the bottom. You might have to go into like the three dots, the more menu to get those. The slides I will put into the Zoom chat as a PDF here in a moment. They will also be emailed out to you after today. It will take a few days for us to process the certificates of attendance, and then we'll send those things out with the resources. We'll also include the link to our YouTube page and those other videos that I was talking about. And then the last little announcement that I have is Chuck has agreed to also do a little workshop for you guys about the Pave Express software, which helps you do some pavement design, some asphalt pavement design. And that webinar is coming up in a couple of weeks. So with that, I will stop talking and I will let Chuck take it away. Thank you again for being here, Chuck. And let's talk a little bit about asphalt pavement design.
Well, thanks, Ingrid. Yeah, I didn't graduate from Michigan Tech, but I am a Michigan Tech dad. My son graduated from there a few years back. So welcome, everybody. We're here today to talk about asphalt pavement design. What are the goals of any kind of pavement design, whether it's asphalt or concrete, composite, anything you're doing? Really, the idea is we need to design the pavement structure in order to withstand cumulative effects of traffic and environment for the life of that pavement. And we want to do so while minimizing life cycle cost and maximizing user benefit. So we want to, do the best thing we can. We don't want to over design things where we're, wasting money, or we don't want to under design things where we've got to have a bunch of extra future maintenance in order to keep that pavement in good condition. So those are the keys that we're trying to do here. So when we talk about asphalt pavement design, really layers are necessary in order to provide, protection for weak subgrade materials or whatever we're building over. How does a flexible pavement work? There's two functions. We want to provide sufficient pavement thickness above any material to prevent any permanent deformation, like rutting, those types of things, or settlement of the pavement. And we want to provide enough surface thickness in order to prevent fatigue cracking. So we want to make sure that as the pavement is standing up to loads, that repeated loading isn't causing the pavement to crack. And that can happen if we're too thin. So, and this is done through a layered approach, again, to distribute that load over weaker materials below. There are different types of design methods. Empirical methods, those are typically based on experience. Experienced pavement managers, over the years have figured out that, hey, I build a pavement that's this thick over a base that's this thick, and it seems to work just fine. And that's one way to do it. Regression based on road tests, these are typically you've done some test sections and kind of quantified how that has performed or how it will perform over various traffic levels and things like that. That's kind of like our AADT method, which we'll be talking about a lot later. Mechanistic empirical methods, or ME, it's kind of the newer design methodology. And I'll talk a little bit more in detail about that right now before we get into spending most of the time I'll spend on kind of the AASHTO method. But when we talk about mechanistic empirical design methods, we're really looking at mechanics of materials. So it's a heavy engineering intensive way of looking at pavement design. And then we're coupling that together with observed performance. So it's an iterative process. There's a lot of intensive testing in order to characterize material properties that we're using in our design. The traffic is looked at a little differently than just a traffic count or types of vehicles. It really gets into tire spacing and how those how mechanistically that tire spacing and pressures and weights all impact the stress it's imparting onto the pavement. So we call that with our load spectra. So we're looking at load configurations, contact path or contact patch areas of the tires. So depending on the size and the tire pressure, there's different contact path um, um, sizes. So it really gets into a lot of input. Um, and I see you are okay. Are you recording already? I didn't. Yes. Okay.
Yep.
I didn't see. Now I see the little record button. Okay.
Thank
So,
you for
um,
reminding me if I hadn't been.
oh, okay. Yeah, I didn't see it earlier, and I was going to say it, and then I forgot. So, and then also with the ME design, there's an integrated climatic model. So, depending on where you are, there's over 1,000 weather stations that get hooked into your specific location. 1,000 different weather stations throughout the U.S. and Canada. Um, and so that gets integrated into your specific location, and there's all kinds of climate history there. So that goes into the process as well. And really, what we're trying to do is predict what types of distresses that a certain pavement design is going to um, end up with over its design life. Um, it is adaptable to new conditions. The ME programs do a lot with local calibrations. So based on your local materials and different things in your specific area, you go through iterations and calibrations. There's a lot of different inputs, which we'll see here in a minute. So this is just kind of a flow diagram showing what I just kind of explained. You've got you it's a little bit different if you are familiar with the AASHTO design method, which I'll talk a little more in detail about, where that gives us a pavement thickness. Here, you've got to kind of start out with a pavement structure, and then based on your load spectra and your um, climate and your material properties, that's all analyzed and predicting how much distress you're going to see at the end of that life. So it's an iterative process. If you have there's thresholds on different types of distress like IRI, fatigue cracking, faulting, different measures like that. Then if it doesn't meet at the end of the design, then you gotta thicken up your pavement section and then run it again. So it's an iterative process. There are quite a few states now that are using the ME design process. It first came out in the early 2000s, and a lot of states have looked at it over time and have been implementing. Here in Michigan, the Michigan Department of Transportation has implemented it. I've got a couple of slides here kind of showing the timelines. They started reviewing back in about 2006. They first implemented it in 2014, so they took about 8 years of study, trying to look at how can we gather all of these inputs that are needed for it. So there were studies done by universities, a lot of material testing, gathering of information, and all that. And then software was released, and they started using that. They used it for a couple of years, and then they stopped because they were kind of used in global settings. When the AASHTO ME first came out, it was kind of global coefficients that people were using and things like that. And people quickly realized that, oh, we need to locally calibrate this stuff so that we get um, more designs that kind of make sense. They were seeing some designs that were pretty wild. Some of them super thin, some of them super thick. It just didn't seem to make sense to a lot of people. So they launched into doing those correlation or calibrations and gone through a bunch of different versions of the software and incorporating different calibrations in that. So they're on version 3 right now, and they're already working on version 3.1 and 3.2. So it's a continued iterative process. This next slide kind of compares the difference between what types of inputs are needed between the AASHTO 93 and the ME design. Um, Really, you can see the basis for them. The AASHTO 93 is an empirical, basically from the 58, 59 AASHTO road test. Mechanistic empirical, like I said, it's the theory of mechanics of materials and how they interact with each other. Um, you've got the original calibrations, mechanistic empiricals using um, LTPP, which is long-term pavement performance test sections from around the U.S. and Canada. There are hundreds of them that FHWA had looked at over a long period of time to kind of see long-term performance predictions. We talked about the traffic characterization with AASHTO. You're using equivalent single axle loadings. With the mechanistic empirical, you're using the axle load spectra. Um, the big thing, material inputs with the AASHTO, there's very few. So it's simple. You got your traffic and things that will go through. And with the ME, there's many. There are hundreds of inputs for characterizing asphaltic materials. Um, so there's a lot of calibration that has to be done, a lot of testing, like I said. So that's kind of the prohibitive part of using ME for kind of local roads and designers and things, because a lot of local agencies don't have the resources. MDOT has spent millions of dollars and a lot of years going through all of this to calibrate their ME design software in order to be able to use it.
And
Um,
I also just want to call attention to, not only are there many inputs that you have to put in there and they have to be calibrated, the accuracy of those inputs, of the many inputs that you have to put in, is important, because it will throw your end result off as well. Whereas with the AASHTO design, there's less things that you have to know, and you have some windows of these are reasonable numbers to put in there, even if there is something that you maybe don't
oh,
have an exact number for. It's a
yeah,
little more forgiving.
yes, a little more simple, we'll say.
Yeah.
um, Yeah, so that's kind of in a nutshell a lot of the differences there. So really, I'm going to talk mostly in this presentation about the AASHTO design methodology because, I mean, with empirical, that's based on your own experience. You're kind of just designing things like that. ME just kind of wanted to give people a flavor of that. There's a lot of inputs there. It takes a lot of time in order to properly calibrate that system for a use where you can get something out of it. So um, we'll focus more on the regression analysis and the AASHTO method, since that's most popular method of doing pavement designs. So road test regression models, these were well-controlled experiments using regression techniques to develop performance prediction equations, widely used, like I said, like the AASHTO guide. There were a few road tests before the AASHTO road tests, which the AASHTO design guide is based on. Got a couple slides on those. The first real kind of known road test was the Maryland road test. It was done in 1941. It was on a concrete pavement. There were 4 different axle loadings they did on the concrete pavement. It was like a mile long, wasn't like really um, a long a long process of even looking at it, but they just wanted to kind of see how loads affected things. And the findings they got, obviously heavier weights, give us more distress. Pumping occurred on plastic clays, and vehicle speed affected the pavement response. So all those things kind of intuitively make sense. Uh, the next road test was the Washoe Road test. This was done in the early 50s in Idaho. Um, it was similar to the Maryland road test, other than this was on a flexible pavement, and some of the findings were the same or similar: heavier weight, more damage, um, distress heavier in the outer wheel path. So this led them to think that, hey, maybe we should be, strengthening up our shoulder materials on the edge of the pavement, um, and identify critical spring conditions. You got to look at your conditions over the whole year, because it seemed like in the spring during the thaw, that's when your support was the weakest. Um, and they also found deflections are a function of speed, temperature, load, and moisture. So they got a little bit more out of this one. Um, and then the Asher Road test, which most engineers that have had any kind of pavement classes are familiar with. Um, we all kind of went through the AASHTO pavement design in class in college. I still have my old binder, and with all the nomographs and all that on it. So, but it was based on the Asher Road test, and this was built in the late 50s, early 60s in Ottawa, Illinois. Um, the soil, at the time they thought that was uniform and representative of kind of a large portion of the United States. They had 4 large and 2 smaller loops. So they built loops outside of the freeway there where they could run traffic around these loops. So they subjected it to a lot more traffic over a longer time. And they had a lot of different variables that they were looking at: pavement thicknesses, the loads that they were putting on there, so load magnitude, environmental effects, because it was a multi-year thing. So it did go through some heating and cooling periods and freezing and thawing and all that. And really, this introduced the concept of serviceability. Um, and that's, how is this road? How serviceable is this road? How long is it going to last? Kind of give them a seat of the pants, way of quantifying that. And really, like I said, this forms the basis of the AASHTO method. Some of the findings of the Asher Road test for flexible pavements: distinguish performance by base type. Again, the better your base is, it seemed like the longer the pavement was lasting. Performance did differ in the inner and outer wheel paths. So again, you got to make sure that we're designing that whole pavement structure, especially fixing up those shoulders. You can't just have your base in that underneath your pavement section, especially when you have heavy loads on the edges. Rutting occurred as shear failure, and cracking occurred during cold weather. So they found, some of that stuff, and spring deflections were the highest in that thaw condition. So a lot of the same stuff. So that brings us to the AASHTO design guide. When we're looking at the AASHTO design guide, we need to know a lot of things. But some of the things that, it's kind of based on is like the resilient modulus to select your layer coefficients. So it does take into some mechanics of materials. It's not just, this road lasted this long with this load, so we're going to interpolate that out. You got to look at design reliability. So statistics is factored into this. Like how much of a percent of the time are you going to feel like, yeah, if I design it here, I want to be 95% reliable, 90% reliable, that, I'm going to meet that goal for service life. Drainage was considered. They understood the materials underneath the hard surface of pavement really make a difference, and we need to get the water out from under those pavements so that we're not seeing that pumping and movement. And then you got to factor in environmental factors: frost heave, swelling soils, thaw, weakening, all that stuff. You need to account for that. So the information needed when we're going through an AASHTO design, we've got to look at serviceability. That's that, PSI, the serviceability ratings. You've got to know where you're starting and what your terminal serviceability are. So that comes up with your change in serviceability. Your analysis period, that's, how long are you looking at for this pavement? How much traffic am I subjecting it to see if it's going to last that long and to design the thickness to stand up to all that traffic. Traffic is a big input, definitely. We got to quantify the traffic and that. Effective soil, roadbed soil resilient modulus. You got to know what we're building on. Uh, that's kind of a starting point for, what you're building on top of it.
Chuck, when we're
Modulus,
looking at, sorry
yeah.
to bust in, but when we're looking at the analysis period, the traffic, are there some minimums that AASHTO requires you to, regardless of what the road is going to be, to design to? Do you have some flexibility
There's
on
some
that?
guidance. Yeah, I'm going to cover that more in
Okay,
detail here in the next slides. This is just kind of a little guideline of
I'm
all the
getting ahead of
things
you.
we need. Yes.
All right, if folks,
Yeah,
if
we're
you've
going
got
to talk about
questions,
each one of these in more detail.
folks, if you've got questions as we go through, please go ahead and put them into the chat or in the Q&A, and I'll bust in and ask Chuck.
Yeah. Modulus of the different layers, drainage, desired reliability, and overall standard deviation of input parameters. So we'll touch on each one of these in a little more detail. So when we're talking about serviceability, there's two parts of serviceability. It's kind of the functional performance. That's your, how does it feel? The ride quality. It's kind of a subjective rate part of the rating. And then you've got the structural performance, what type of cracking or rutting, different distresses are we seeing out there? So, um, and so with AASHTO serviceability, you've got your pavement serviceability index, PSI, that we're looking at, and that correlates to those physical distresses. It's a 0 to 5 scale, 0 being impassable, and 5 would be perfect, a brand new pavement. The recommendations on the AASHTO serviceability for initial PSI is typically 4.5 because I guess, nobody's building perfect pavements out there. um, it's just kind of the standard. It's probably got a little bit of a factor of safety type of thing in it. Anytime engineers put stuff together, there's factors of safety built in. So, terminal PSI, really, what's my terminal? During the ASHO study, when they were looking at the PSRs, most panelists and that thought that, somewhere between 2.5 and 3, by then you're getting to the point where it's probably, you got to look at, we better probably do a rehab to this road. So the recommendations, 2.5 to 3 for major highways, maybe go down to a 2 for lower classifications or 1.5 for minor highways. Really, that gets to, obviously, the bigger your delta between your initial and your terminal serviceability, the thicker the pavement's going to be because it's going to be out there longer, subjected to more traffic in that. So,
We've got a question in the chat. Is there a
yeah,
relationship between PSI and the currently employed PASER rating for asset management?
I guess you could almost say it's almost like a half scale type of thing. Um, it's it's probably similar because a PSI of 5 would be like a pacer rating of 10 where everything's perfect.
Right.
So if you're starting out at an initial PSI of 4.5, which most designs I've seen, that's usually where you start. That's like a pacer rating of a 9. So it's very good, maybe not perfect because nothing's perfect.
Yeah. Right.
And then you get down to like a 2 pacer rating or a PSI of 2, that'd be like a pacer rating of 4. So it's very similar. Yes. Created for different things, I think, but yeah.
Right. Right. Different purposes.
So we talk about the design period, and really what we're talking about here is the length of time the design is intended to last before the pavement reaches the end of its serviceable life and requires rehabilitation. So Design period may vary based on the type of roadway. I've listed, these here are kind of the design periods that are suggested for different types of roads. High volume urban, um, you should look at 30 to 50 years. High volume rural, maybe 20 to 50. Low volume paved, 15 to 25 years. So that's something that you have to decide in the beginning, because when you look at your traffic and all that, it's going to interpolate and grow that traffic out further. So the more traffic you have on those pavements, the thicker they're going to become. So traffic, traffic really, it's the primary design input with the AASHTO. You could have, different base materials in that, but if your traffic changes a lot, it can really affect that overall thickness of your pavement. So getting traffic information, it can be a complex problem. Uh, you've got your traffic volumes, your average annual daily traffic. If that's not readily available, what do? You can go out and do some traffic counts and things like that. Um, you know, there's different ways of getting traffic. There's maybe some traffic maps available. Maybe you don't have the exact traffic on your road, but maybe it's similar to a road that might have some traffic data on those maps. You can look at that. But it is key that you do have a good idea of what your traffic is, because not only your average daily traffic, but you've got mixed traffic in there too. And you really need to quantify what types of vehicles are driving over that, because there's a lot of difference between really heavy trucks or school buses or passenger cars, or, all the different vehicles there. So variable vehicle and axle weights. We got to look at lane distributions, things like that. If you got a multi-lane roadway, so how many, which direction? Maybe sometimes roads have more heavily loaded traffic in one direction and lighter loaded traffic in another direction. Now, we don't usually typically we wouldn't design the northbound lanes different than the southbound lanes on a 2-lane road, but
You would want to make sure you have that
you want to make sure you
understanding
have that
of the full
information.
understanding of the
Yes.
problem. As somebody who has done some pavement designs with data where we'll get the traffic to you later, it is very difficult. You can't sharpen your pencil as much when
Yeah.
you don't have really good traffic data. So I would encourage folks to make sure you have the traffic data before you are moving on to that pavement design portion. For
Yeah.
everybody's sake, you will get a better product, and you also, whoever is doing the pavement design, will be a happier person.
Yes,
And I
definitely.
also, while I'm mentioning that, we did have a traffic counts webinar last September. It's on our YouTube page, and I'll drop that into the chat here in just a second when I find it.
Yeah. And then we also have to predict the future. So, sometimes you're in an area of high growth, and maybe that traffic over the next 20 years or 30 years, whatever your design period is you're expecting it to grow a lot. And that's important to know, because obviously if we don't put in a growth factor, that we could grossly under design that pavement. Or if we overestimate the growth, sometimes you can design that pavement. And things like that. So that's all part of it that goes into it. So again, the information, the average annual daily traffic, directional distributions, percentage of trucks in design lane, all this kind of gets into what AASHTO uses for traffic are what we call equivalent single axle loads. So those are 18 kip equivalent single axle loads, and they do this through load equivalency factors, and we'll get into that. And then obviously we've got to estimate the growth rate for our road, and is that a simple or a compounding growth rate? So looking at lane and directional distributions, we're typically going to, like I said, we're not going to design the northbound and the southbound lanes differently. We're going to typically design for that heaviest loaded lane. So that could be directionally, or if you got a multi-lane, in each direction, we're looking at that design lane. So typical assumptions, directional distribution, you assume it's 50-50. unless you have data that tells you otherwise. Lane distribution, if you have multi-lanes, here's some, kind of guides on how to, decide, if you don't know specific lanes, if you got 2 lanes in one direction, you can assume, 80 to 100% of that traffic is in that design lane. If you got 3 lanes, it's 60 to 80, or 4 lanes, 50 to 75 are in that design lane. And then we get into, what are load equivalency factors? Really, it's trying to equalize all that traffic into an amount of damage that's being done to that pavement. So we got to look at the mix of our traffic and then apply a load equivalency factor, because obviously a passenger car isn't going to do as much damage as an 18-wheeler, fully loaded going down the road. So I've got kind of an example here. You can see the passenger cars are very small as far as load equivalency factor. Single unit trucks 0.6, double units 1.5. So these are being multiplied by, so you're getting like the 1.5 on the double units. That's like 1.5 times that 18 kip load. So and then you got the trains, those are like your double trailers and that. And you could have other things. A good example of that is, up in the UP, you've got logging trucks and things like that. Or if you're near an asphalt plant, you got the big asphalt haulers that are, those loads are going to be special. They're not going to, equate to these normal load equivalency factors.
Maybe the street in front of your fire station too. Fire trucks can be one of
Yeah,
those heavy ones as
they can
well.
be a heavy one too. Yep.
I got a question for you, Chuck, about the lane and directional distributions. Do you design, like if you've got a center left turn lane, do you design that the same as the travel lanes, or is there a little bit of change to that?
You're typically going to design the cross section all the way across the same thickness and that. I mean,
For constructability
for
reasons.
constructability, for, you got times where if you are doing maintenance or something and you're shifting traffic and things like that. So to try to get to a point where you're designing, those auxiliary lanes, or maybe not your truck lane, the same thickness in that, it's hard to control where the
Yeah.
traffic is, but you're just trying to estimate where the majority of it's going. So kind of a good example, MDOT is getting into building these flex lanes.
Mm-hmm.
And so on the freeways, they're kind of widening these shoulders out and building those up. And sometimes those are not as, structurally thick as the main part of the freeway.
Yeah.
So they put signs up to limit, trucks being on it and stuff. And then it's only open certain hours of the day. So they're expecting a lot less traffic out on that. So
Okay.
you could design it a little bit less, but then you get into how do you police it, how do you control it, all this.
Right. Right.
Yep.
All right. Good. Thanks.
Good. So then we get into predicting the future, and we kind of covered why this is important. Is you don't want to be under designing or over designing your pavements. Next, we get into the material characterization, and we've got the unbound materials. These are your base layers, your subgrade, and we can characterize those by tests or classifications. When we're talking about subgrade, there are soil classification maps if you don't have tested material that you can use as a general guide. And then there are, the A1 through A7 classifications there. And then you can, kind of use a estimated modulus value based on those. California bearing ratio, R value, triaxial shear tests. Those are all tests that you can do on actual materials. And you can look at those and kind of convert those into resilient modulus values. Because really that's what, when we're talking subgrade soils and that's what we're really looking at for that resilient modulus value. If you get into testing like in-place materials, in-place pavements and things like that, the falling weight deflectometer, if you have access to one of those, you can go out there and thump the pavement and back calculate what that modulus value is for the different layers too. there are guides in the AASHTO. Well, this isn't a guide. This one here, um, you want to you want to take into account your climate. And so when you're going through the astro design process, you might your roadbed soil modulus, especially in your subgrade and things like that, may change over time. So I remember using this when we were in school. You got, how it changes month by month. And then, you can see how that, affects your relative damage. So you adjust that modulus that you're going to use for design. A lot of times, maybe you're using that worst case. What's my worst month? I'm going to design for that, and I'll be good for the rest of it. So, and MDOT, typically their modulus values for subgrades, they range from 3,000 to 10,000 is their kind of typical values. So, you're getting up into the 10,000, you're looking at really good sand. Subgrade, the 3,000, the really soft silty clays. So those are gonna, the lower that number, the thicker your pavement above it's gonna have to be. And kind of back to that first slide, we build in layers to kind of protect those weaker soils. Like I said, if you do have some of the tested materials, there are kind of correlation diagrams in the AASHTO design guide. And so that you can convert those numbers to a modulus or a structural coefficient. Some of the typical values that MDOT uses for structural coefficients, dense graded ag base, 0.14, open graded, 0.13, sand subbase, 0.10. So those are kind of the structural coefficients that we use in the AASHTO design guide to give that structural value based on how thick it is. You multiply it by your structural number, and that gives you that total structural number value that you sum together to try to make sure that we're protecting the subgrade below and meeting our design. The hard surface layer. So in our case here, we're talking about asphalt pavements. So the asphalted concrete pavements, typical structural values. AASHTO, the typical value was 0.44 for asphalt materials. Here in Michigan, we use 0.42. So we're a little conservative on that. Some other states range from 0.44 up to 0.54. There's been some studies with, the new materials and different asphalts and things like that that are used in different areas that, they've increased those structural numbers up. So here in Michigan, we are up to 0.42. That changed about 3 years ago. Michigan used to, for their base courses, be at 0.36. And that was kind
for
of
those of you who are outside of Michigan, we do allow higher vehicle weights. So that is something to be aware of. If you're like, what
yes.
are they doing? Why are they using more conservative numbers? There is some method to the madness. So
Yes. And one of the reasons we adjusted the base up from 0.36 to 0.42 is our base mixes now are designed the same way as our top course mixes are. So they're all designed the same way. Used to be, I think, way back in the day, it was more of a bituminous coated aggregate base. It wasn't. So, but they've also used some of the ME software and testing and all that to verify that, yeah, we can bump that up and we're not going to have a performance issue. So next thing we'll talk about is drainage. Obviously, water is a problem with any pavement. It can reduce the strength of unbound materials, both our base and subgrade, which can cause pumping of fines, loss of support, can cause stripping of the asphalt even, if the asphalt's submerged underwater for a long time. Differential heaving and frost heave. So drainage is a big thing to look at as well, and the AASHTO really covers that. There's a lot of material in here to think about, and really to characterize the materials that you're using. Make sure that you're using the right drainage coefficients as well. So general design considerations, we want to obviously prevent water from entering the pavement structure. So we should design our shoulders and adjacent areas to make sure that we're draining water away from those, and that they're maintained. If we could have a shoulder that's draining water away, but if we're not maintaining along the shoulder and water's getting trapped there at the edge of the shoulder, that can cause issues as well. Um, and we want to provide drainage to remove that water quickly, um, and build a pavement strong enough to resist the effects of water and load. So Astro design guide recommendations, they kind of quantify their drainage as far as the quality of drainage. So excellent drainage, what they consider excellent drainage is 95% of the water is going to be removed within 2 hours, down to very poor where it won't drain at all. So there's excellent, good, fair, poor, and very poor. And there's numbers there, to look at that. When we're talking about drainage, also the percentage of time that that layer approaches saturation is critical. So it's not just that the water will drain through it, but how much time is that being saturated, because it acts differently at full saturation. So, and then we get into looking at how the time of saturation and the quality kind of affect what our structural layer coefficient, our or our M values for drainage are. So you can see excellent and not very saturated, you're up between 1.4 and 1.35. If you're down in the poor and it's greater than 25% saturated, you're at 0.60. So that's just, you're going to modify that, your structural layer coefficient based on the drainage of those layers as well. So then we get into reliability, and really reliability, what we're talking about here is how reliable is our pavement design and performance. Um, you know, how is it going to perform over time due to traffic and environmental conditions? So we want to be assured that, X% of the time, we're not going to have a problem sooner than we want. So we're talking about statistics, probabilities, and that. When we look at, the Astro recommendations, obviously we want to have a higher reliability on our, high volume urban freeways typically, and maybe we can live with a little lower reliability on local roads, in urban areas and things like that. So, or rural areas. So you can see typical ranges, 85 to 99.9 on interstates and freeways, 50 to 80. They're pretty wide ranges. Typically, I mean, most pavements that I've seen have been involved in designing, you're typically between 80 and 90, even for the local roads. I mean, you're not going down to that 50. I mean, unless you really want to try to save costs and that, but that could cause headaches in the future. So, and then we get into overall standard deviation. And this variable defines how widely our two basic design inputs, traffic and performance, can vary. So, we kind of go into all this stuff and we've got reliability, but things can vary. We might be off a little bit on the traffic or off a little bit on, our performance. Maybe we're off on our growth or things like that. So there's an overall standard deviation. Typical values are between 0.4 and 0.5 for asphalt pavements. When we get, most of the time, I've always used 0.5. I mean, the range in ASHTO is 0.54 to 0.5 for flexible pavements. I think it's 0.35 to 0.4 for concrete pavements. Typically, we use 0.5 for asphalt and 0.4 for concrete pavements. So it's just that conservative nature of engineers.
Would there ever be a situation where you would use 0.4? Like, can you think of a reason where you would reduce it?
Maybe, I would think intuitively, if you have a lot of confidence in,
Yeah,
your input, maybe you could go down to the 0.4. I mean, you could play around with it and see what it does to your thickness. I
yeah,
don't think it would affect it a whole lot,
right, right. So
because of,
again, to keep that nice warm fuzzy feeling about your design, maybe just
yeah,
stick to 0.5.
yeah. So we take all these inputs and, going back to my college days with the ASHTO design methodology, we had all these nomographs, and you take these inputs and you draw your lines across, and you come up with a overall structural number. And then you can take that based on your structural numbers of your base materials and your asphalt materials and come up with a base thickness. Or if you want to say, I'm using 8 inches of ag base and 1 foot of sand sub base, then you multiply those by your coefficients and then figure out what my overall asphalt thickness is. And your structural number should be higher than this based on putting all those together. So this kind of shows that. So we're adding up all those structural components based on the depth of each layer, and that total structural number has to be greater than what we came out with in the nomograph. Um, so really, in summary, pavements are designed for the public, so we want to make sure that we're doing the best job that we can, because people are going to be using these roads for a long time. So regardless of the method, we need to know traffic, environment, materials, variability. These are all inputs that we kind of need to know ahead of time. And then understanding the interaction of how those parameters, affect our design is really going to lead to a rational design. If you're not, familiar with or don't want to go through all those nomographs and stuff, there is a simple pavement design tool. It's called Pave Express. It's really an app. You can put it on your phone, your tablet, your computer, and it's an easy way of going through and doing pavement designs based on the AASHTO method. And we will be, as Ingrid said at the beginning, we'll be having a design workshop on January 22nd on Pave Express. So tune in then to get more details on that tool and how it works. And we can even have some extra time that we've set up for that to kind of go through some examples, and we could have questions and see how it adjusts things, and we can play around with it a little bit.
Yes.
So.
And I did just drop the link to register for that class into the chat if you are interested. We do
Great.
have a question in the chat. Do you know of any studies done of extending the pavement life by applying a cool coating? And maybe, are you familiar with cool
Cool
coatings?
coating. I'm not sure what that is.
Yeah, if you want to give us a little bit more info, maybe we can look into that. If anybody else has any questions, please put them into the chat. I will put the survey in right now since I'll give you a little bit of time to fill it out if you need. But we will hang out here for a little bit while you fill out the survey. If we have other questions. This is a question again. Solar reflective coatings was the question. Extending the life of pavement by applying a solar reflective coating onto it.
Yeah, I'm not familiar with any studies on that. I'm assuming it's to kind of resist the heat getting into the
Yeah,
pavement type of
I know
thing.
it's been used
Um,
in some urban areas.
mhm,
I'm not off the top of my head familiar with any studies,
yeah,
but I know I'm now that you say it that way, I do understand what you're talking about.
yeah.
Maybe that's the subject for a future talk here. We can get some experts in to talk
Bring
about it.
some experts in and see how it works.
Yeah. There's another question in the chat. Does this method work if there's an existing composite pavement where you would be replacing the asphalt on top of concrete? Can you use that AASHTO design method for a composite pavement?
For an overlay, yes, you
Yeah.
can. Yep. You can use the AASHTO method for an overlay. There's an overlay module in the Pave Express, actually. So basically what you do then is you're not starting from scratch. So you're kind of going to quantify what those coefficients are of the existing materials. And typically they've degraded, and a lot of it will depend on how much cracking, what types of distress you have in that pavement, and there's a way to kind of reduce that existing structural number that then you're overlaying. So then based on how long do you want that overlay to last, what's my design period and my traffic, you can figure out what that required structural number is. And so then you've got that minus your existing that you've kind of reduced down to what's left of your pavement structure. And then that tells you how thick your overlay has to be. Yep.
Awesome.
It's very similar.
Yeah, one of the comments here is about the, with the solar reflective coatings, maybe preserving that binder from UV degradation, which, it makes sense that that could lead to a little bit longer extended life. My familiarity with those coatings is more for the cooling effect than any um, life cycle reasons. But yeah, I will make a note. We'll see if
Yeah.
we can get some info on that one. When we're talking about the those modulus values, Chuck, what are some of the ways that you could get those values? I know some of the soil testing, taking a regular like standard penetration test, it's hard to get those values in those upper layers, especially if the layers are thin and know what blow count relates to which layer. Are there other test methods, like maybe the dynamic cone penetrometer? Is that going to get you closer to doing something? Um,
Yeah, and I'm not really a geotechnical
yeah,
engineer, so I don't know exactly how all those tests correlate to each other, but, like, I know that, um, for instance, in the Astro method and also in the Pave Express thing, if you know the R value or the CBR, there is,
yeah,
like, an equation that you can equate that to modulus.
yes,
Um And then, so as far as what soil tests you'd need, the triaxial shear test comes to mind because that's kind of a common one that was in the presentation here and stuff like that. You can kind of figure that out.
yeah,
There are a lot of guides. A lot of times I'll tell people, the soil classification types, you can look at those maps and see kind of what, the prevalent soil is in the area if you don't have an actual sample. Um,
yep,
that's a good starting place, and then adjust it based on your climate and your your drainage situation, because seasonally that can vary, and then you kind of
yes,
want to make sure that you're covered for that.
for
Uh,
sure.
and you can look at your frost depth, mean frost depth in the area and things like that, and how far down in the section that is, if it's frost susceptible material or not. A lot of those things can go into it as well. So it's not an exact science that, oh, if I got
Right,
this soil classification, my number is 8500,
right,
or
right, right.
these are it's all things you got to think about.
Yes. And one thing I would let folks know, if you are doing an R value test, there is a lab test for that one. It does need a decent volume of soil in order to do the test. And so that's something to think about if you are going to be doing soil borings. Your standard 5 foot shallow pavement soil boring is probably not going to get you the volume of soil that you're going to need. So if your geotechnical engineering consultant or your lab testing company or whoever is poking extra holes, they're trying to get more volume of soil for you. They're not trying to cheat you, I promise.
Yeah.
There's a question here about cold joints. So during some maintenance operations, a crew may create a cold joint between lanes. And does the design's thickness still hold up if you got that cold joint now that you've created? Is that going to be a problem?
Yeah, I mean, that's kind of the way that we build things. I mean,
Right.
we kind of know that that's kind of a weaker area. How we've dealt with it here in Michigan is we have a joint density specification, and there's been a focus on making sure that those joints aren't degrading. Um, so I mean, that's not really factored into the Astro pavement design. There was, some consideration of, when they did those original road tests, that we got to make sure that we've got something, designed on the shoulder so that, the edge of our pavement doesn't just stand up against the
Yeah.
subgrade, because they saw that that's where the highest concentration of loading was and damage was. So it's important that we do have, a good shoulder that's maintained next to it as well, and that you extend that base under the shoulder as well, because that's part of your pavement structure. It
Right,
doesn't
for
just
sure.
end at the edge of the road.
And like you mentioned as well, that that drainage is going to be really important. So ditch maintenance, culvert maintenance, all of this goes into, you can build the best pavement possible, but if you don't have some of those other pieces in place, you can still end up with some performance issues in the future. We
Yeah.
got a question in the Q&A. Does the average temperature for an area factor into the specifications and design? Which,
Yes,
yes,
it definitely
yes, it
does.
very much does.
It yeah. I mean, because that's gonna, affect how much time it's wet or in the wet freeze zone and things like that. And temperature probably affects more, um, when you're placing the asphalt too. I mean,
Yeah,
construction of the asphalt itself, but it also affects those materials, and if you've got more freeze thaw cycles in an area, because it, ranges from really cold to warmer to really cold to warmer, then you're probably going to end up with a thicker overall pavement section in order to protect more material. Now, it depends on what your materials are, your subgrade materials, but if you've got poor subgrade materials, your pavement section is going to be thicker to protect those more because you've got that worse situation as
right.
far as temperature and drainage and all of that.
All right. I did put the SurveyMonkey link in. That's how you'll get your certificate of attendance. It also has a short evaluation of today's session, so you can let us know what you thought of it. If you've got other topics that you'd like to hear about in the future, we'd love to know what those are. Chuck, thank you so much for today's session. I really appreciate that you do these, and I think our audience also really appreciates it. If there's other questions, we'll hang out here for a little bit, but otherwise, thanks everyone for joining us today. Make sure you grab that SurveyMonkey link. I can drop it in the chat again if you need it. Like I said, this is being recorded and we'll have that posted soon, as well as having that sent out to you in the next week or so. So thanks everybody. Thank you again, Chuck.
Thank you, Ingrid. Thanks, everybody. Have a great day.
Yes. And yeah, we've got that workshop coming up as well. So that'll be, what is that, in a couple weeks? Is it
January 22nd.
the
Yep.
22nd?
Yes.
So that will be a couple hours long. It's not a lunch and learn. That one will be from 9 to 11 in the morning. We do plan again to record that one for you guys. And so if you can't make it on that day, you'll still have a chance to see the content. That one is also a free webinar for you. So we're trying to make you get the best bang for your buck here for all of these.
Yeah,
But yeah,
and it'll probably be more like about an hour of presentation, and then we've got the second hour is more for questions, or if people want to kind of look at different scenarios or try different things within the software, we can bring that up and kind of do that.
and it looks like a few folks are having some trouble with the SurveyMonkey link. Let's try this link and see if that one works for you. Sometimes you might have to try a different browser window. Like if you're using Chrome, you might have to use Firefox or Safari or something like that to make it work. But let's try that and see if we can get that to work. There is a question in there, and I believe it still works like this, where it asks you if you are attending with other people, and it won't let you continue on if you don't put the number 0 in. If you try and put like, no, I'm not, it won't let you, it won't accept that as an answer. It has to be the number 0, and then you can move along. So again, I appreciate it if you try and do that right now, because then if you have any problems, I will hopefully be able to help you. But if you need to jump off, you can grab the link and fill it out anytime in the next day or so. And we got 24 hours to fill it out and you'll get your certificate of attendance. So it does take us a little bit of time to process that. So it won't be an instant process, but within the next week, you'll get an email with that, as well as the slides and a link to the recording and all of that good stuff. And if you've got questions as you are going through the year, Chuck is available, and that is what he is there for, is to answer questions. You can also send, if you got a question and you're like, I think this might be dumb, you can send it to me and I can anonymously send it to Chuck. We are happy to do that
There
as
are no
well.
dumb
So,
questions, like you
yes,
said before. The only
there
dumb
are
ones are
no.
the ones you don't ask, right?
Exactly, exactly. So thanks everybody. Like I said, you're free to go for today's session. We appreciate that you attended and we hope to see you at one in the future, but thanks so much. Otherwise I'll give it about 5 minutes here and then we'll close down the room so you can have a little bit of time to make sure you've got that link. But again, thanks everybody. Thank you to Chuck, and we'll see you next time.